Hi, so quick note about the video that's going to follow. During the development of this project, not much footage was shot because I never thought I would actually make a video on it, but after the end of the project, I decided it might be worth posting. So some shots might be rough around the edges, but I still think it's a video worth watching and the project is really interesting, so I hope you enjoy it.
I have been playing pool much longer than I have been smoking flux and getting lead poisoning. And all this time has made me an incredible pool player. I said it has made me an incredible pool. Oh, damn it! Okay, so maybe I'm not as good as I remember. Or maybe I just need a bit of practice. But to play pool, you really need a friend to play with you, and that's just cruel. So I have two options. I can either A, go meet people who like pool and force them to play with me, or instead of spending the summer out in the sun sitting in the Greek beaches, I could stay inside, design, manufacture, and program a robot that I can play pool with. So the option seems pretty obvious to me. So in the past, I've made a bunch of robots whose job is to beat people at board games, robotic arms destroying people in chess, as well as embarrassing children in Connect 4. But there is a big difference between these games and pool. The games I mentioned earlier give the computer an advantage due to them being inherently better at computing the future game states. Pool, however, is not a game of thought, but a game of dexterity and accuracy. A game which is made to be played by humans. So making a robot that can play pool competently is much harder compared to those previous projects due to having to beat humans where brain power is not the be-all and end-all and dexterity and consistency is much more important. So let's break down the project into three main parts. First, we have to know where each and every ball is in relation to the table. Then, after finding all the balls, we must locate the white cue ball and calculate the best shot we can take to have the highest possibility of sinking one of our balls. And finally, we must make a robot that can go to the white cue ball, position itself properly, and take the shot with accuracy of less than a millimeter, while also being able to navigate around the whole table without disturbing any of the other balls. So, doesn't all that sound easy? No? No? Good, because it's not easy at all. So, let's start with the camera. Now, the computer vision program has two main jobs. One is to locate all the balls inside the table, then get us their coordinates with millimeter precision, and also, after finding all the balls, we have to separate them into solids and stripes and find the white cue ball and black 8 ball. So, how do we find the balls in this image? Well, OpenCV has many ways to find and locate circles in images like hue circles and contour-based detection. However, at this distance, most that we tried didn't prove extremely reliable due to the dullness of the edges. So we moved on to the hottest trend in computer engineering right now, AI. Nah, just kidding. Or am I? We decided on running YOLO, a widely used and thoroughly tested computer vision machine learning algorithm. So, to start, we need to train a model. Generally, for model training, we use RoboFlow, which makes the annotation process really easy. We start by placing a bunch of balls on the table, then we take a picture, we move the balls around the table, and then take another picture. We do this for about 100 to 200 pictures and import them into RoboFlow. Then we annotate the pictures one by one, and then we export the database and give it to our training server, which after a few hours, it spews out our weights. A model like this can be trained on any computer, however, we use a server with an NVIDIA Tesla GPU to be able to iterate faster on models. Now, with our model at hand, we can run the program and voila, we can find where the balls are on the screen. But this is not that useful if we can't find their centers accurately. To get that, we get the ROI around the detected ball and then do a Gaussian fitting, which can find the center of the ball very accurately and consistently. So we have the center in pixels, but how can we correlate that into XY table coordinates? So a camera doesn't see our world like we do, it sees it like this, which would make accurate measurements impossible. To fix that, we can take pictures of a pattern with known dimensions and then give them to a calibration program that then spits out some matrices that we can use to fix the distortion. Now, let's address these funny looking images here. These are called our UCO markers. These are essentially a simplified QR code that holds a single number and can be easily read out by cameras. Around the table, we place these markers at known locations. Now, with the markers and the distortion matrices from before, we can run an algorithm called PMP. Using this, we can correlate pixel positions to the XY coordinates of the table. Finally, we need to categorize the balls. To do this, we train another YOLO model, but instead of finding the balls, we need to classify them into the required categories. So, as before, we take many pictures, annotate, train, and we have another model. Now, with both our models combined along with the Gaussian fitting and PMP, we can find the location of the balls in relation to the table and tell them apart. Now, this might sound simple, however, I have dumbed down the process a lot not to make it incredibly sleep-inducing. If you want more details, there are very good resources online talking about everything I mentioned above. So now that we know the location of all the balls and their type, how do we get to the white cue ball and strike it to hopefully sink another ball? Well, before we get into the robot, let's take a look at some basic pool rules. The aim of American pool is to first sink either all the striped or solid balls using the white cue ball, and after that sink the 8 ball first to win the game. The balls are originally placed using a triangle, and one of the two players must break them to start the game. Some shots are harder than others. The difficulty of a shot is rated by the angle the cue ball needs to hit either a solid or a striped ball, the distance of the balls to the pocket, and if a bank shot is necessary. Another element of pool is a foul. For a foul to be given to a player, one of the following criteria must occur. Either a player sinks the cue ball, they make a shot where they hit no balls, or they make a shot that first hits one of the enemy balls or the 8 ball. So we need to construct a robot that can achieve all the actions stated above. After some brainstorming, we ended up with a robot comprised of an XY gantry, similar to that of a CNC router, and a head that is able to pick up the cue ball and place it anywhere in the table when a foul occurs. It also needs to have some way of striking the cue ball with variable force and place a striker in any position around the cue ball. Our first design looked like this. The head had 3 main elements. The striker, which used 2 servos to lift it up and down and rotate it with conjunction to the XY system and some inverse kinematics, it would in theory be able to strike the cue ball anywhere. Then we have the suction head, which can pick up and drop the cue ball and be moved out of the way when it is not needed. Lastly, we have the electronics bay in the back that contains the brain of the head. We will talk about the electronics more, but for now let's focus on the mechanics and a bit more about the striker. It is a very simple contraption that went through a few iterations. We wanted to make it entirely electromechanical and not use any pneumatics. So our way of accelerating the striker are these 4 springs here. There is a metal plate connected to the back of this part and an electromagnet that when energized can pull back the striker using the motor that transfers power through this lead screw. We can choose how much force the striker is producing by how far back we pull the spring, and after we have pulled them back as needed, we can strike the cue ball by turning off the magnet. Lastly, there are these limit switches here, which can detect when the magnet is touching the metal plate, which lets us reset the system by just moving the magnet until it hits the limit switches. The design in theory would work. However, after a lot of trial and error, we were never able to properly calculate all the offsets needed to have the striker hit the ball exactly where we wanted at every angle and position. We tried using a solid-state lidar placed on the head to locate the ball and make small corrections, but this was also proven not to be very effective due to the reflectivity of the balls. It should also be mentioned this was quite a rush project. It had to take less than 2 months from start to finish because we had to take this to an exhibition, which meant we had a hard deadline. So, after spending 2 weeks on this head design, we decided to redesign it with the aim of reducing the work needed to center on the white cue ball. So, after 2 days in CAD, we ended up with this design, which ended up being the one we used. Its main component is this 5-to-1 gear reduction. It used this XL430 servo in extended positioning mode to be able to accurately move the striker around the white cue ball, which would always need to be in the center of this gear. The striker is mounted to this assembly, which we named the plane for what I hope are obvious reasons. This assembly was able to move the head up and down while also rotating it in the Z-axis to make shots that would otherwise be blocked by the wall or other balls. So this design is better, but how can we make sure that the cue ball is always in the middle? Simple, we cheated. This device here is the same as the pump on the previous head that is used to lift the cue ball. However, we realized that it can also be used to center it for the striker. Now, some of you might say that's cheating because we slightly move the white ball. But the white cue ball movement is not premeditated or used to make the shots easier, and with only 2 weeks from the exhibition, we had to move on to other things. But most importantly, our game, our rules, so shut up. Now, we have a camera that can find what ball is where, and a robot that can move anywhere and strike the cue ball to hit any other ball. Now, we just need to glue them together. So with knowing where everything is, how can we find the best shot available? First, we find all the ways the white cue ball can strike another ball, which results in that ball being pocketed. Now after that, we start grading them based on weights that we set. Those include the distance the cue ball has to hit the target ball, as well as the distance between the target ball and the pocket. We also weigh the angle the ball needs to be hit at, and we look at where the white ball will end up, and lastly, if a bank shot is needed. All these weights are generated by reference weights that we set, and after all that, we get a mess of a graph that makes no sense to us, but makes sense to a computer. Now we solve this graph, and the lowest score of the path is our shot. For the foul, we also calculate all the shots that can be made from every position the white cube ball can be, and we add that to our graph. The algorithm is written in Python, and our own physics engine is written in a language called Python, which is like Python with memory control. That lets us make a very fast physics engine, which can be easily integrated with the main Python code. Now note that this explanation is very top level, but getting deeper here will make even the nerdiest nerds bored out of their minds. Also, I should note that this method is very similar to the way that stuff made here used for his pool robot, so huge kudos to him. Incredible as always, Mr. Stuff. Lastly, I want to say a few words about the XY system and the electronics. The movement system is made in the cheapest way possible. For the X-axis, an XL belt is used along with an NEMA 17 motor, and for the Y, a rack and pinion system is used with two NEMA 23 stepper motors. All axes ride on V-slot wheels, and the X and Y axes are connected by CNC aluminum plates. This makes for a cheap and sturdy enough system for this application with acceptable accuracy. What let us get away with this kind of movement system is the fact that the rigidity doesn't really matter because no strong forces are applied until after the shot is taken, and any inaccuracies can be corrected by the Ryuko's here, which the camera can locate within a millimeter precision. The stepper motors are driven by two DM542s for the Y-axis and a TB6600 for the X. All these are powered by 24-volt power supply, and the step and direction signals are generated by this OpenCR. This job can be done by almost any microcontroller, however, we use the OpenCR due to its ready-to-use CAN bus communication that we would use to talk to another OpenCR placed in the head, so we only have to run a 12-volt power to the head, which comes from this PSU, and an Ethernet cable that carries the CAN bus signals. In the head, the OpenCR controls all the serial servos with its integrated controller, turns on and off the suction pump, and controls the striker motor, along with communicating everything to the OpenCR in the control board, which in turn talks serial to a NUC computer, which runs Ubuntu that we use to run the camera and the main algorithm, along with a simple GUI for control. All the code that runs on the NUC is written in Python, except for the physics engine, which is in Python, and the OpenCR code is written in C++. So now we connect everything together and we get this. There are still a few problems left to solve. Well, after a while, all the things that can go wrong run out, and we are left with what's a mostly functional robot.
Δεν το έβλεπα όμως ακόμα. Δεν ξέρω αν το πιες το βίντεο.
It's still by no means perfect. It could maybe use one more month of development to iron out all the kinks, but for the time being, I am very happy with how it came out. Now, all that's left to do is to take it to TIFF and have people play. So in conclusion, am I happy with the final result? Yeah, I would say so. For the time we had, most people said we wouldn't even finish in time, so I am glad we were able to get a playable version done within the 2 months. As mentioned above, if we had one more month of development time, I believe all the small bugs could be ironed out, but hey, I can't complain. I want to say a massive thanks to the 3 other people that helped me with the development of this project. I couldn't have done it without you. So, thanks to George, who did the camera and the communications, to Dimitris for the solver algorithm and the GUI, and to Anthony for the constructions of the camera rig and the lights. So, thanks for watching. If you enjoyed the video, please leave a like. Next is probably more Colgan content, which will soon make its first full power shot, so if you care to follow along with that, please consider subscribing. Thank you for your time, and goodbye!